Power System, organized by MNIT Jaipur under the EICT Academy invitation. It is my pleasure to introduce our distinguished speaker of this section, Dr. Deep Kiran from IIT Roorkee. He is known for his expertise and contribution in power system regulations, power system optimization, power system flexibility, and network clustering. In today's session, he'll be sharing his knowledge and insights on the topics relevant to optimization. On the behalf of this organizing team, I warmly welcome Dr. Deep Kiran and thanking him for taking the time to share his valuable expertise with us. Sir, we are honored to have you with us now today. I now request you to kindly take over the session. Thank you, sir.
Yeah, thank you, Jyotika. Just a second, I'll try to connect the where I can. I'm trying to connect the. So, is it okay if I switch off the camera because I don't know if the bandwidth is okay with everyone at the audience side.
Okay, sir.
Okay, and or I'll keep it on because I'll be moving to the other board and where I'll be writing it on the PPT also.
Okay, sir. No issue with that.
And can attendees speak or?
Their chat box is open, sir. You can see them from the chat messages. On the audio will be also available for them, sir.
Acha, okay, but they cannot speak.
Yes, yes, sir.
Oh, okay, okay. Uh, okay, so then what I can do is I need to. Wait, let me share my screen. Okay. Okay, can you see the screen if you can confirm?
Yes, sir.
Perfect. Let me also then join from my mobile or so that I can keep seeing the chat messages, whatever they are messaging. Uh, okay. So okay, good. I can write also here. Uh, So, hello everyone. I hope all of you can see me, sorry, at least see my slide, and also you can hear me properly. So, just I'll try to rearrange everything so that you can also see me. Just perfect. Now you will be able to see me as well. Perfect. Perfect. So, just can someone type if everything is fine? You can see me as well as you can see the slides. Perfect, perfect. Okay, so I'll be so please. I want this session to be made as interactive as possible. So please try to type in the chat whatever questions you have and try to be as interactive as possible because it's a 2 hour session. Um, can we can make it interactive and make it interesting. Okay, so let's start with. I think you have already got the idea about linear optimization, right? I got to know you have covered that. So can you just confirm in the chat? Are you aware of linear optimization? Okay, good. So So we will see about the nonlinear optimization. Before jumping into nonlinear optimization, I just want all of you to quickly answer this question for me. So if you can quickly read this question and can we all try to frame the optimization model for this question? So I'll give a minute. So the question says a farmer has recently acquired a 110-hectare piece of land. He has decided to grow wheat and millet on that land. Due to the quality of the sun and region's excellent climate, the entire production of wheat and millet can be sold. So we are assuming in this question that the quality of sunlight and the climatic conditions are perfectly efficient or perfectly okay with in terms of wheat and millet production, right? And he wants to know how to plant each variety in the 110-hectare land, right? And the costs, the net profits, the labor requirements are given in the table below. So, and also the farmer has a budget of 10,000 rupees and availability of 1200 man days during the planning horizon. Find the optimal solution and the optimal value, right? So, can you please help me in developing this optimization model? How do we do that? So, let's say, so do you all got the question? Can you tell me what should be the objective function of this optimization model? Perfect. Okay, so Gaurav is saying we have to maximize the profit. I would say, Jyotika, is it okay if we can allow the audience to speak because there are few people and we can easily make it interactive. Uh,
Yes, sir, I'll make them. to speak, sir.
Because otherwise typing will not be convenient for all of them.
Okay, sir.
So in the meanwhile, till Jyotika tries to figure that out. Okay, good. So Yangadatta mentioned the profit maximization is 100x1 plus 200x2. Okay, so let me just go here and so so we have cost of millet and wheat, that is 100 and 200, right? This is the one. What did I? Okay, wheat is 100, millet is 200. So this is 200, this is 100. Okay, and profit is 50 and 120. So profit is 50 here, 120. And mandates is 10 and 30. 10 here, 30 here. And the total budget what farmer is having is 10,000 rupees, right? And total mandates is 1200, right? So these are the inputs given. So the what should be the variable here? Hello.
Am I audible, sir?
Yes, yes, I can hear you.
Sir, am I audible? जी, good morning, sir. Sir,
Yes, yes.
variables may be millets and wheat. If we have to minimize the cost, increase the profit,
Okay,
maybe.
perfect. So now the audience can speak. Uh, wait, I'll just. Hello. So we are meeting for the first time. When you speak, please do let me your name so that I know you also. Please, what's your name?
Sir, my name is Anand, sir. Anand Pandey.
Okay, Anand. Great. So what you mentioned is you meant what was your answer? Sorry, can you please repeat?
Sir, if we want to minimize cost, increase the profit, variables can be millets and wheat.
Millets and variables means millets and wheat. What about millets and wheat in variable?
It's like, sir, you have written cost of the column wise, you have written cost of millet is 200, right, sir?
Okay.
And wheat is 100. The
Okay.
objective is the millet and
Okay. So basically, okay, got it. So Anand mentioned that the objective should be minimization of cost, right? Whereas I saw in the chat box that there was another person, Gaurav. Can you unmute yourself, please? So Gaurav mentioned that. Acha, okay, okay, no problem. So Gaurav mentioned that he wants to maximize the profit. So the profit. So question is now, which one is correct? Either the uh, uh, profit or the cost.
Sir, both are, I think, related with each other, sir. Profit will only be increased if you minimize the cost.
Okay. Uh, but uh, actually, we are given net profit. Is it net of cost? Uh, no, actually, it's why it is not. Okay, Ratan is saying that the quantity. So let's quickly come to the question again and observe that although it is net profit is given, so net profit means uh, he is basically by selling the product, what profit he is generating from selling of wheat and millet. But this cost is actually in terms of the purchasing of the seeds for wheat, the seeds for millet, the water requirement. So all those things are the cost, and that's the budget, right? And that's where the budget will take the role. So again, what Anand has said and what Gaurav has said, and even Ratan has said, always remember this in an optimization problem. I'm sure you have studied now the basics of it. That we always go for maximize the profit if the data and if the information is available. We will always go for maximize the profit. Whenever we talk about an individual, so you think yourself, keeping yourself at the center point. For example, let's say you want to manufacture a product. Let's say you are building your own startup, right? And you want to manufacture something. So the idea should be to maximize the profit, not to minimize the cost. If let's say, idea is, if let's say you want to manufacture a product which on obviously if you install or if you put lot of money in buying good quality of raw materials, then what will happen, that the cost of production will increase, right? So let's say if you have a good quality of let's say raw materials and everything, then your cost of production will increase, right? On the other hand, because the cost of production has increased, your selling cost, if you increase that, then only you will be able to increase the profit. But the problem is, because the selling cost you cannot increase much, because the customer should be ready to pay that much amount, the customer will basically back out and they will not be able to buy. So always the agenda is to maximize the profit whenever you are going in terms of individual context, or you are going from an industry point of view or a company point of view. You always have the objective of maximize the profit, right? Always remember this. Whenever you are going for the personal benefit or a company's benefit, you should always do maximize the profit. That's a basic understanding. Now the question is, who will then do minimization of cost? who is that entity who should think of minimization of the cost? Anyone? Okay. Durga says manpower cost by farmer. No. My question at this moment is what? Who should? I don't know why it is not doing. Some problem is there. Anyways, so then my question is, who is that entity who will go for minimization of cost? Consumers. Okay. Consumers can go. Can you elaborate, Satyanarayan? Can you unmute and speak? What do you mean by consumers? Under which context? Cost effectiveness and minimization of cost for best product purchase. Okay. Okay. So generally, uh, as a consumer, whenever think, let's say think from the electricity point of view. What you mentioned, Satyanarayan. If you think from the electricity point of view, our electricity tariff, let's say the price of electricity pi is fixed. We are the residential consumers, right? We as a residential consumers, our price is fixed. Let's say uh, it's in I am in Roorkee, so in Roorkee it is 6.5 rupees per kilowatt hour. This price is fixed for me, for the residential customer in Roorkee. Right now, because this price is fixed, now if I want to operate myself or I want to consume this electricity, we always want to minimize the cost because I can only minimize my electricity bill by reducing my consumption. Right? We can only reduce our cost by reducing our consumption. So that is the main reason. Because this price is fixed, I cannot do anything in terms of price. So as an individual entity, I have to do minimization of the cost. Good, Satyanarayan. Also, if you also think in terms of in a broader perspective, whenever government uh, comes up with a policy or comes up with some planning, they will always look for minimization of the cost because government does not run for profit. They do not do a business for profit, right? So government will always look for the minimization of the cost, right? So these are some of the factors. Now coming back to this question here, here we have already mentioned that the information is there where we have already given the information for the net profit. So consider me or yourself as that, as you can put your foot in the shoes of this farmer and think in his context because he is doing a business, right? And the ultimate goal of a business is to get the profit. So let me just erase a few information from here and okay. So I hope now you got the idea. So also somebody already mentioned the variables here should be the let's say I keep W hectare land for wheat and M hectare land for uh, millet, right? So I keep this. So these are the variables because the question says that the farmer wants to know how much hectare of the land he wanted to install wheat and how much portion of the land he wanted to install millet, right? Or install, I'm saying, or growing wheat or millet, right? So basically, the objective function now, as Ratan has correctly mentioned, it is 50W plus 120M. That is going to be my objective function. So you see, you try to understand, let's say if we, in a practical context also, you will always get, you will never get a question directly or an optimization model or something. You have to create an optimization model based on your information. That's how different consultants, advisors in any industry or in a company, they operate in that manner, right? So now, what should be my constraint? What should be my constraint? Okay, so Ratan has mentioned 100 W plus 200 M should be equal to 10,000. One is this. Another, what Ratan has mentioned, that is 10 W plus 30 M should be equal to 1200, right? Is it all or do we need anything else here?
So we could add W plus M should be less than equals to 110 hectares.
So W plus M less than equal to 110. Perfect. And also both W and M should be within the range of 0 and 110, right? Individually, you cannot grow wheat in more than 110 hectare of the land because the farmer is anyway having only 110 hectare of land, and you cannot grow millet also in more than 110 hectare of land because again, farmer is having only 110 hectare of land, right? So, do you see any problem here, or it's completely fine? Does it look fine to you, or is there any problem here? I can tell you there is a problem. Okay. Anyone able to guess? Screen sharing stopped. Okay. Okay. Can you see it now? Okay. Perfect. Perfect. So do you see, Ratan? Can you unmute and you can only tell? Can you see any problem here, or is everything fine? Okay. Okay. let me just try to explain you the problem here. Let's try to solve this thing. Okay. Infeasible solution. Good, Satyanaran. How do you guess that it is going to give an infeasible solution? Let me just give you an idea. So this is the website where you can easily draw any equations. So okay, let me try to create the expressions, right? Uh, So the first equation was 100x plus uh, 300, sorry, it was 200. Y is equal to 10,000, right? Let me zoom out this equation. Are you able to see the screen, right? Then,
Sir, the screen sharing is stopped, sir. Kindly check it out.
oh, acha, again, I don't know what is happening. Okay, so are you able to see it now?
Yes, sir.
Okay, perfect. So this is the Desmos, and here I'll be showing you how the curve will look like. So one equation we had was 100x plus 200y. I'm keeping this as x and y because w and m is not possible in Desmos. So x and y, and this is, should be equal to 10,000, right? And this is how the line of equation will look. So let's assume the x-axis is x, which is w, wheat, and y-axis is m, millet, that is basically y here. Now the another equation was 10x plus 30y should be equal to 1200, right? So this was another equality equation. Now we mentioned that x plus y should be less than equal to 110. Right? Do you see how these expressions has came? Now, when we try to maximize our objective function, that was 50x plus 120y. So let's say I keep this as 0. What we want that this line should be as maximum as possible. I have to increase the line in this direction where you can see my pointer. So as I keep moving up and up, this will try to maximize my objective function. And wherever the last point in this search space, it will intersect, that will be my maximum objective function. Now, let's say why, so maybe I think who mentioned Ratan or someone, x plus y less than equal to 110. Why can't we keep this as equal to and not less than equal to? Anyone? Why we are keeping x plus y less than equal to 110 and not equal to? Can I keep it? To leave some land empty. Why do we want the land to be empty? He has to always go full 110 hectare. Okay, Satyanarayan saying is he has to always go to 110. Rutvik say won't be able to satisfy all three equations and at once optimal may be less than 110. Perfect. you guys are actually thinking in the right direction. We cannot keep it equal to 110 because I think what one of you has mentioned, that it is not necessary that this budget of 10,000 rupees what he has, that farmer is having, is sufficient to grow all the plants and all the 110 hectare land. It may not be sufficient, right? In the practical sense, we cannot say that. Similarly, this 1200 is also may not be sufficient. 1200 man days. So man days means basically how many either one man can be used for 1200 days to produce that, or 1200 men can be used for one day and it can be used for producing wheat and millet, right? So the man days concept is number of person required into the days, so that is man days, right? It is very common from the industry point of view. Now for on the similar context, it is not necessary that this 1200 man days will be sufficient for producing all the wheat and millet, right? So basically, when you mentioned this, the error was we cannot keep everything equal. We want it to be less than equal to and try to figure out the maximum optimization problem. So let me just give you a even simpler understanding of it. Let's say only x plus y equal less than equal to 110. That is the objective function. Now, what should be my maximum profit? Consider only one constraint, that is x plus y less than equal to 110. So what I'll do, I'll try to increase, I'll increase it to 2000. Okay, I can increase it further. I can increase 5000. So you see this blue line, it is still within the search space. I can further increase it to, let's say, 7000. It is further within limit. I can increase it to 9000. It is within limit. I can increase it to 10,000. It is within limit. Let me increase it to 12,000. It is within limit. Let me increase it to 14,000. It has crossed now, right? Because even the x-axis is between 0 to 110. Y-axis is also 0 to 110. So you see here the point is 0 to 110 and it is 110 comma 0, right? So the maximum what I can do here is 13.5. No, it should be 13.3. No, so if I zoom here, I have to reduce it. If I reduce it to 13.0, 13.1, maybe 13.20, yes, 13.20, I think, yes. So you see here, my maximum objective function value is 13,200. And what is the solution in this case? The what farmer is doing? He's only producing, you see the solution here, x is 0, y is 110, right? So now I'll actually create, because this basic understanding of optimization is very important. So when we have, sorry. So when we have 50x plus 120y, maximize subject to x plus y less than equal to 110, right? So if we have just this constraint, you see, and it is obvious, right? Because the profit is more in producing millet. So x comes out to be 0 and y comes out to be 110, right? Now what I'm doing is I'm adding in this same objective function, that is maximize subject to, I'll keep this constraint and I'll add the budget constraint. Now, can you guess which is the optimal solution? What should be the value of X and Y? And here the profit was 13,200 rupees. That was the profit. Can you tell me the profit in this case? Quickly, can you go to Desmos and try to calculate the value? Let me help you out here. So let's say I'll add one more constraint regarding the budget constraint, and this was 200Y and 10,000. So you see here, this budget is anyway not sufficient to grow the plants, wheats and millets in the complete area, right? So now my profit has reduced to maybe 6,000. Yeah, okay. Is it exactly 6,000? Yes, it's exactly 6,000. Right? So you see here, when you have just the budget criteria, that is of and the land criteria, the X comes out to be 0, the Y comes out to be 50, and the total profit is 6,000 rupees. You see, just because he did not have the sufficient budget, you see how the profit has dropped. And obviously, it is more beneficial to grow millet, because millet gives a profit of 120 rupees compared to 50 rupees of wheat. He is preferring to install or grow millet in this situation. Now, let us come to our original optimization problem in the third case, right? So, this is our uh, third case. This was second, this was first. Now, let's say in our third case, what should be X and Y? Can you quickly tell me? Let me help
So
you out.
W and M.
Yes. What should be the value? Anyone? What should be the value of X and Y in this case? And what should be the profit? Okay, let me help you out. Okay, 4,800. Ruth say 4,800. Okay, let us just do that so that everybody can follow me up. So I'm adding a man days criteria. Now you see when I add the man days criteria, so follow the blue line. Blue line is actually the objective function line, right? And now this blue line is actually crossing. So your feasible space is just the y-axis, the x-axis. Now with this line from 100 comma 0 to this midpoint, that is 60 comma 2, and then your area space is from 0 to 40. So I'll just I'll just freeze this and this. Sorry. Wait. So this is your feasible region, right? Now, what should be my objective function? If you see here, if I try to maximize it, let's say if I take it to 5,000, I still see there is small margin which I can increase. I can, let's say, go to 200. I can still see the margin. 300, I can still see the margin. 5,400. This is the perfect intersection, what is happening. And now the solution is basically 60 comma 20. Let me come to this, and you can now appreciate the concept here that the solution comes out to be 60, 20, 50, and the profit comes out to be 5,400. So you see here, it's very interesting. You see, observe that the profit was reducing as you were adding the constraints, but he was always interested in producing the millet because millet was giving more profit. But when you added the man days criteria, you see how he has shifted to wheat compared to millet, and he is able to get the profit has not reduced to that much. It has just reduced 6,000 to 5,400, and just 600 rupees has reduced. But he has shifted his interest towards wheat compared to millet. Do you observe that? So basically, I took time and gave you the understanding how basically an optimization problem is important, and how do we visualize an optimization problem, right? Till 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 it is a linear problem, we can easily do that because it was a linear problem. Why we say linear? Because the objective function is a linear, all the constraints are linear, right? So we can easily visualize it. Also remember that never put equality equation. Equality equation basically forces an optimization problem to give a particular value, which we cannot do, right? Because in practical situations you have to give the freedom that uh, let's say for example, in this case I would have made x plus y equal to 110, but we cannot do that because he does not have sufficient budget. If I do x plus y equal to 110, then it will give an infeasible solution, right? So I hope you got the understanding of an optimization problem, that you always and always give a inequality equation, never give an equality equation until and unless it is exactly mandatory. Then only you go for equality equation. Otherwise, we never go for equality equation, right? We always go for inequality equation. Good. Now, I think anyone has any question till now? Because then I'll move to nonlinear. So, okay, no one is writing anything, or you can write also. I'm also seeing the chat box. If you want to speak, you are free to do that. Okay, so till it was a linear problem, we can easily visualize. We have seen everything in Desmos and tried to visualize the problem. But when the problem becomes non-linear, then it becomes even trickier to solve. Then it is not that easy to solve the optimization problem. then we need to do something, right? So I'm sure we can write an objective function fx which we want to minimize. Let's say it's an unconstrained optimization problem. There is no constraints, right? No inequality, no equality constraints are there. In that case, how do we optimize, or how do we get the optimal value of x when we want to do fx? So the idea is very simple. I'm sure all of you know that you take the first order derivative and equate it equal to 0, and you calculate the value of x from this equation. Whatever value of equation value you got, will that value be a minima or of fx or maximum of fx?
Sir, it may be both maximum or minimum.
Perfect, perfect. So you need to do perfect. So good. So all of you are writing. Ratan is writing. Okay. So we need to. We cannot say the value of x we got is what we do not know that. So for that we need to go for a double derivative, and it can be maxima, it can be minima, or it can be a saddle point. Saddle point is basically when you have some things sort of this. So this point is minima, this point is flat, so that is this is basically the saddle point, this is basically the minima, and this is basically the maxima. So a function can have all three characteristics, right? Then, so we have to take the double derivative, and based on that double derivative, we can figure out whether it's a minima or maxima. There can be, there is another concept called local and global optima. So so for example, let's say, I'll draw a function. Let's say I want to solve, and let's say this is a 3D plot. Here we have x, here we have y. This is the function x comma y, right? So here you can visualize that there are two minima points. Whenever you have more than one minima point, we call them, all the points are local minima, right? And among all the local minima points, there will be one point which we can see from here. This is basically the global optima point or global minima point. This is the local optima or minima point, right? Now question is how to figure out which one is global and which means this. You can, for visual inspection or for this small problem, you can definitely visualize and tell. But for a practical problem, how can you tell which point is local or global? Can we, is there a way, or so practically, I can tell you from the must defined range. Okay, within a range, we can say whether a problem is global or local minima. But I can tell you from a practical context that there is no way you can find out how many local optima points are there in an optimization problem, and or you can also do not found cannot find the global optima if you have multiple local optima. So till now we do not have any method to figure that out, right? So we cannot do that. That's the problem of nonlinear optimization problem. And you can imagine, let's say you get this solution, right? For this solution, x is this, and maybe the y is this value, right? And for this solution, the x is this and the y is this, right? So problem is basically, especially when we talk about economics, let's say stock market or financial markets, if you get multiple solutions then there will be fight among players that which solution you will offer to them, because each solution will have different financial implications on the players, right? You are able to visualize that, because this system will operate at x value and y value, and this system will operate at x and y, these particular x and y values. So it's a tricky thing to do, and this is not possible as of now in the concept of optimization. We have to bear with whatever setup we have at this moment. So basically, we basically you if you start from this initial guess, you will reach to this local optima. If you start from this initial guess, you will reach to this optima. If you start through this minimum point, you will reach this global optima point. So it depends on what initial guess you give. It depends on the range, what you mentioned, what Ritviz has mentioned. So it depends on a lot of factors. So now, once we have once you know, only when we have the objective function, you know how to solve this optimization problem. But now, let's say I add one equality constraint into this. That is minimization of fx subject to gx equal to 0. Now, to solve this equality optimization problem, we need to convert this optimization problem into this Lagrange function. He was a French mathematician. He proposed that we can convert any optimization problem having minimization of fx subject to gx equal to 0. We can add fx plus this lambda and gx, where this lambda is actually known as Lagrange multiplier, or we can also call it as dual variable, because the x is basically the primal variable. Right? So if you write this optimization problem in this fashion, L equal to fx plus lambda gx, now you can see that this has become an unconstrained optimization problem. You need to minimize L, not F. And you will have to minimize this to get the solution of fx subject to gx. This is how we convert an optimization problem with constraints into an unconstrained optimization problem. So for this unconstrained optimization problem, that is L, our criteria will be, we have to take the derivative. So now L has two variables, right? X and lambda. Now, if we have two variables, you have to take the derivative with respect to X, which will be the partial derivative of fx plus lambda into the partial derivative of gx, and equating this equal to 0. And also, to convert this optimization problem into an unconstrained optimization problem, we have added a variable called lambda here. So we also, because this is also now part of this optimization problem, so we also need to take the derivative with respect to this lambda also. And although because lambda is just present with gx, so eventually you will get gx equal to 0, which is nothing but your equality equation. Right? So once you solve these two equations, and because these two equations are basically, it is like ax plus b is equal to 0. It is of this form. So you can just take basically you can solve these equations easily. Is it okay to solve, or it is difficult to solve? Let's see through an example, so then you will get the feel of it. So let me just tell you the graphical illustration, And obviously this gradients of fx and gx must be collinear. This I'll show you through the illustrative example. Let's take this problem. Uh, there is an objective function which is 0.25 x1 square plus x2 square, which is subject to 5 minus x1 minus x2 equal to 0. So I have made the objective function quadratic or non-linear, whereas my constraint is still constant or linear, right? Now, can you tell me what will be the solution of this problem? So for that, you need to first form the Lagrange function. It will be 0.25 x1 square plus x2 square into lambda 5 minus x1 minus x2, right? Once we do that, we have formulated this problem into a unconstrained optimization problem. Okay, so Rutvish says the solution will be 5 and 0. Okay, Rutvish, let us try to solve this. So here, how many variables we have? X1, x2, and lambda. So what we'll do, we'll take the derivative with respect to x1. We'll get 0.5 x1 minus lambda equal to 0. We'll take the derivative with respect to x2. That will be 2 x2 minus lambda equal to 0. And we'll take the derivative with respect to lambda, which will be 5 minus x1 minus x2 equal to 0. So now we have three variables and three equations. So let me just get the value of x1 from here. Wait. So x1 is equal to lambda by 0.5. From here, x2 equal to lambda by 2. And I can put this here minus lambda by 0.5 minus lambda by 2. This will give me lambda equal to, what will be the value of lambda? So it will be 1 by 2 plus 0.5, right? So this will be 2 here and 2 plus 1 by 2. So this will be 5 by 2, right? And 5 by 2. So basically 5 into 2 by 5. This will come out to be 2. Am I doing the right thing? So 2 to 4 plus 1, 5 by 2. And this is equal to 5. So 2 by 5. So this will come out to be 2, right? Am I doing the right thing here? Okay, good. Then the x1 value will be 2 by 0.5, that is into 2, that is 4. And x2 will be equal to 2 by 2, that is equal to 1. Right? So you see here, this is the way you calculate an optimization solution or of an optimization problem when you have just the objective function and the constraint, equality constraint, right? So again, I will be writing the same thing here. So I'll not repeat this. So I think we'll just cross check the solution. Right. So x4, x2, x1 equal to 4, x2 equal to 1, and objective function value is equal to 5. Perfect. We got the right answer. Now, if let's say, can you say in this optimization problem, where the solution is lying? So you have 3 points here. This is point 1, this is point 2, and this is point 3. So this is the, or I can tell you for this. So basically this, if you'll see, this is the equation of an ellipse. So I have created different ellipse here at different function value, right? And this is the line having this equation 5 minus x1 minus x2 equal to 0. Now, Can you, okay, so can you suggest or can you guide me this solution what we got will be at which point among these 3 points? 1, 2, or 3? Okay. So Gaurav says 2, Anand says 3, Nirbhay says 2, and Ratan says 2. Okay. So because x1 is 4, roughly it will come here, and this will be x2, that is 1, and here 4. So, and because it is intersecting with the objective function ellipse equation where objective function is equal to 5, the solution is lying at point 2, right? Let me give you another understanding. If you will see that uh, the idea of lambda is basically the derivative of the objective function with respect to x1 and derivative of with respect to equality constraint with respect to x1. And if I do the same thing for x2, my the optimal solution will lie at the point where both the derivative of the objective function and the derivative of the equality equation is collinear. When I say collinear, that means that both the tangents are perfectly in a line with each other. It cannot have a solution here. We cannot get a solution here. We cannot get a solution here. So that was the understanding. You need to just visualize it. You need to understand it, how this collinearity comes. If you see the slope eventually for both the lambdas from both the equations, either I take KKT in terms of x1 or in x2, it has come out to be equal to 2. So that's what it is representing, that it is collinear. Right? Now, let's say I take an example where I have an objective function, but multiple set of equality equations. How will I solve it? In a similar way, now earlier I only had one equality equation, so I only had lambda. But now because we have three equations, I'll have three different lambdas: lambda 1, lambda 2, lambda 3. Right? So we'll have three lambda equations. And because we have three lambda equations, uh, we will take the KKTs in terms of x1 because x1 is one variable. We'll take the derivative with respect to x2. We'll take the derivative with respect to lambda 1. We will take the derivative in terms of lambda 2. We'll take the derivative in terms of lambda 3. Right? And you'll take all these derivatives equate it equal to 0 and solve the equations. You'll get a solution. Right? Now, till now, everything was fine because we did not had any inequality equation. Now let us see what happens if we have an inequality equation. So I'll say that minimization of fx subject to gx equal to 0, and I'm adding an inequality equation which can be nonlinear, hx less than equal to 0, right? And this inequality constraint can be binding or non-binding. So binding means it is hx equal to 0. Non-binding means hx is strictly less than 0. Both is possible, right? Now, to solve this equation, there was a scientist, Tucker. They have proposed a concept, and I can tell you a quick story here that Karush and Kuhn and Tucker, they are not from the same generation. Karush proposed this idea long back And then Kuhn Tucker did this work in their MSc thesis. And when they published this work, they saw that Karush has already done this work. So to honor Karush also, they have developed, or they always mention, if you do Google search, you'll find out that they always mention Karush also in this, and they call it as KKT conditions, right? So yeah, sorry. Okay, so so they proposed KKT condition. So KKT, we can, with the help of KKT conditions, we can solve this optimization problem. How do they solve it? Is basically the idea is same. They form a Lagrange function where they are saying Lagrange function is fx plus lambda gx plus mu hx. What does this mean is, till here you already know how we did in our previous case, right? They say that we add this mu hx also here in the Lagrange function. Now the idea was is obviously you have now three variables x, lambda and mu, but when you take the derivative, you will take the derivative in terms of x, you will take the derivative in terms of lambda, but you will not take derivative in terms of mu. Why? Can you think, if I take the derivative in terms of mu, it will give me hx, which is equal to 0. Now the problem here is that hx can be equal to 0 if it is binding, but hx can also be strictly less than 0. When we take the derivative with respect to mu, this will force the hx to be equal to 0, and it will never give me a solution where hx is less than 0. Do you see why we do not take the derivative with respect to mu? So therefore, instead of this, what they proposed is a complementary slackness condition, where they say that the product of mu hx should be equal to 0, such that mu is greater than equal to 0. What do I mean is, consider this at optimality. Let's say when you have reached the optimal solution, what will happen to this lambda gx? At optimality, lambda gx will be equal to 0, right? Because gx is anyway ensured to be equal to 0. And at optimality, because we actually want to minimize fx, right? We do not want to minimize L. And we want the minimum value of L such that fx should be minimum, and these two terms, lambda gx and mu hx, should not be present. So therefore, this should also be equal to 0. Now, to keep that, to ensure that, what they say, you add this equality equation in addition to this, which is known as complementary slackness condition, where you keep mu hx equal to 0 and mu is greater than equal to 0. And what does this mean? Let's say if this is a binding constraint, that is hx equal to 0, then mu will be not equal to 0. If it is non-binding constraint, hx will be less than 0, and mu will be equal to 0. So that's what we are forcing the problem to solve an inequality equation. Let us try to do that through an example. I'll take the same example, right? Where the objective function is 0.25 x1 square plus x2 square. And this is my equality equation. And this is my inequality equation, right? Now, how to solve this. If you see here, I'll come to this later on. So I just wanted to ask from here where the solution will lie, but I'll come to this later on. So the solution is we will form the Lagrange function in the same way we did earlier. That will be the function plus lambda into omega, that is the equality equation, plus mu into g, that is the inequality equation. So I'm just actually few terms have changed. So this is omega is equality equation, g is inequality equation, right? Uh, and so I can write my Lagrange function as this, right? I've just put the value from the previous. Now, at optimality, we'll take the KKTs in terms of uh, x1, we'll take in terms of x2, we'll take in terms of lambda, and we'll keep this equation, which is mu into this should be equal to 0. Now, how to visualize it or how to solve it? What we can do here, this equation or this inequality equation can be either equal to 0 when mu is greater than equal to 0, or g can be less than 0 where mu is equal to 0. These are the two conditions possible. Now, for these two conditions, let's say I call this as condition 1 and this as condition 2. When you have this condition 1, this inequality equation is actually has become an equality equation, right? And once you have this as an equality equation, then you can easily take derivative in terms of mu, because it is an equality equation. That is why, please note this, that the first condition is making me making this inequality equation as equality equation. That is why I'm able to take the derivative. So I'll get x1 plus 0.2 x2 minus 3 is equal to 0. So I have equation this as A, this as B, this as C, and this as D. And how many variables I have? I have 4 variables, right? X1, x2, lambda, and mu. I can solve this. Can anybody help me out in solving this? What is the value of x1, x2, lambda, and mu? So let's say I use equation C and D to solve for, so here I'll get x1 equal to 5 minus x2, and I can put there, which will give me 5 minus x2 minus, sorry, plus 0.2 x2 minus 3 equal to 0. This will give me 0.8 x2 is equal to 2, and then x2 is equal to 2 by 0.8, that will come out to be 20 by 8, that is 2.5, right? And then x1 will also be equal to 2.5, right? So I can, from these two information, I can put this in equation A and B, I'll get the value of lambda and mu. So it will be 0.5 into 2.5, that is 1.25, right? 0.5, 0.5 into 1.25 plus, sorry, minus lambda plus mu equal to 0. This is one equation. And then 2x2 into 2.5, that is 5 minus lambda plus zero point 0.2 mu is equal to 0. From here, I can get the value of lambda. So I can just subtract this equation. So I'll get 1.25 minus 5. So that will be 3.75. So minus 3.75 plus zero point 0.8 mu is equal to 0. So I'll get mu is equal to 3.75 by zero point 0.8. And I can anybody help me out? Just a second. Okay, so can anybody tell me the value of lambda and mu? So I hope you got the understanding. You will get the values of mu and lambda, right? Now, this is one solution. And if I go for the second case, right, when I consider that G is less than 0 and I'll get mu equal to 0, I can solve my optimization problem under this condition also. So let me just quickly uh, tell you through, uh, wait, I have to delete this all so that I can. So for your simplicity, I have already given this cases where in one case, I considered this was our first case where we have already considered our inequality equation as equal to 0 and this inequality as greater than 0, right? And we got the solution which is x1 equal to 2.5, x2 equal to 2.5, lambda equal to 5.9 and mu equal to 4.68 and the objective function at 7.8125, right? And the other case where I strictly assume that mu will be equal to 0 and this inequality equation is less than 0. And if I do the same thing, calculations, all the calculations where I keep mu equal to 0, I'll get x1 equal to 4 and x2 equal to 1. Okay, Ratan, can you quickly check how do we do this? Uh, you are 205, 205, 5.937 and 4.68. That is correct. I think you wanted to write 2.5, 2.5. Okay. Anyways, you are right. You are right. You are right. Okay. Okay. Good. 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 Good, Ratan. So now question is these two solutions we got. Among these two solutions, which one to choose? So let's say I call this as solution 2. This is solution 1. Which one to choose and why? Can anybody unmute and say? Anyone? Which one to choose and why? Anand, what's your thought? Anand, Ratan, Gaurav, Nirbhay, Rutviz.
What I guess, we can go with second case.
Okay. Your name, please?
Sir, Anand, sir.
Anand.
My name
Okay.
is Anand.
Second. Okay. You are saying that we should go for the second solution, right?
Yes, yes, sir. I'm sure.
Okay. Why?
Right, sir.
Why?
Because, sir, this G function, sir, the inequality constant is less than or equal to 0.
Okay. You are thinking in the right direction. Tell me. Tell me. So G can be less than 0 also. G can be equal to 0 also. Now, why do we want to choose the second solution? So second means this is my second, this is my first, right? So why second? So okay, tell me what's the objective function value here in the second case? Because we want the minimum solution, right? So x1,
Right.
4, and so it will be 4, 4, 16 into 1 by 4. So that is 4 plus 1. That will give me 5. Right? So we will actually go for solution 2 because we want the objective function to be minimum. And in these two cases, we are getting the solution minimum for the second case. Therefore, we will go for f equal to 5. That is the correct solution, and we will not go for this solution. So this is also a feasible solution, and this is an optimal solution. But this objective function value increases when we force this equality equation equal to 0. So therefore, we will not go for this solution. Instead, we ensure that the solution is. So I'll quickly go back and show you this. So now can you tell me, let's say this is point 1, this is point 2, this is point 3, this is point 4, and let's say this point is point 5. So the solution we got, what we got is actually which point among these 5 points, 1, 2, 3, 4, 5. So this line is basically our inequality equation. This line is our equality equation. So What do you think? Which one should be the point of our solution? Okay, so there is a catch here. Again, to what Gaurav said, just can you see in this equation this constraint, the solution what you got in second, is it actually satisfied? So we want this equation to be, what is the solution we are getting? 4 plus 4.2 minus 3, that is 1.2 less than 3, which is incorrect. You see that when you force this mu to be equal to 0, we want this inequality equation to be less than 0, right? But eventually, this constraint is not getting satisfied. Therefore, I hope now you are able to visualize this. I just wanted to make you guys understand the importance that the solution will eventually shift to this point, and this will not be a solution. So do not jump to the conclusion. You should always see that this inequality constraint is not getting satisfied, right? Therefore, the solution is the first one. Now, can you tell me where the solution will be? So 1, 2, 3, 4, 5. Where the solution will be? Okay. So Gaurav is saying 3. Anyone else? You see, Gaurav, how we moved our solution from 2 to 3 because we did not cross check the inequality constraint in our previous solution, and that was the problem. So you see, the solution should always lie on this side of the this line because this is when less than equal to 0. And also the solution should always lie on this line because this is an equality equation. So the optimal solution will always lie on this line, this equality equation line, and this is intersecting here. So therefore, this is the our optimal solution, and this is the where the optimal point lies, right? Now, the problem with this is basically you have just right now is one equality equation, one inequality equation and one equality equation. But if you, let's say, in a practical setup, we will have many inequality equations, and all these inequality equations, you have to do all these combinations you have to create for all the inequality equations, and you can imagine how much it will be tedious to do that for all inequality equations. So therefore, we have to do some smart way to eliminate this if else type of thing, right? So to eliminate that, what we can do here is basically, let's say this is the generic optimization model. So this is actually known as optimization model, right? Where objective function is minimization of x and u. Inequality equation is g x comma u equal to 0, and inequality equation h x comma u less than equal to 0, right? I'm assuming u is the independent control variable, x is the dependent variable, g is the equality constraint, and h is an equality constraint. We'll see that through this example later on. So to solve this, in a generic sense, there are two methods. One is Newton's first order gradient technique, and it is an easier one. You can easily visualize and easily able to. So this helps in handling of this inequality constraints. How do we do that? It basically converts the inequality constraints to an equality constraints, right? And so, whichever inequality equations are becoming binding means equal to 0, you'll convert them to an equality constraint. And whoever equations are violating inequality constraints, you will add a quadratic penalty term in the objective function. Let's say if we have, for example, in power system, voltage limits are there, reactive power limits are there, or any limits, we can add that as a penalty function. I'll tell you the details through an example so that you appreciate the concept. And eventually, the constraint problem will look like, or the Lagrange function, which is basically unconstrained optimization problem, it will look like fxu plus lambda gxu plus penalty. And this penalty is in this fashion, this quadratic fashion. I'll come to that, how do we represent this for this small problem. Then this method is also known as steepest descent technique, and it is generally one of the fastest way to get the optimal solution. So how do we do that? Is basically we take the derivatives in terms of lambda, in terms of x, in terms of u, right? And then we arrive at a solution which is like this. We will first guess the value of u. You have to take an initial value of u. You will put this value of u in equation 1 to get the value of x, right? That is the second step. Then once you know the value of x and u, you will put the value in this second equation to get the value of lambda. So only unknown here is lambda. And then once you know all the value of x, u and lambda, you put that equation in values in third equation to calculate the value of dl by du. And then you will update the u based on u old minus beta into dl by du, and where beta is the step size, and you will keep updating it, and then you will again go back to the second step based on the new values of u. You will again calculate the value of x. Now, once you know the value of x and u, you will calculate the value of lambda from the second equation. And then once you know the value of x, u, and lambda, you will get the value of delta u. And we'll keep on updating this till this dl by du is less than equal to some tolerance, right? So let's say some epsilon value. Once it is less than some tolerance, you will stop the iteration. This is the step for solving the Newton's first order method. Let me just give you a quick example how, or rather, how to solve this. So basically, we were having this optimization problem 0.25 x1 square plus x2 square subject to 5 minus x1 minus x2 equal to 0. and x1 minus 0.2 x2 minus 3 is less than equal to 0. So this was our optimization problem, right? Now, this optimization problem, if I want to solve it, what I'll do here, I'll form the Lagrange function as 0.25 x1 square plus x2 square plus lambda into 5 minus x1 minus x2 plus I have to add this as a penalty function minus 0.2 x2 minus 3 square into some alpha where alpha can be equal to, let's say, a big value, big penalty function, right? What you will do here, let's assume we take any value, either x1 or x2, we can fix any value. Let's say I fix the value of x1 as 0, let's assume. Now, what I have to do here, as I mentioned, we'll take the derivative with respect to x. What was the first derivative? We'll take in terms of lambda. That was the first step. So we'll take the derivative in terms of lambda here. The lambda, which will give me 5 minus x1 minus x2 equal to 0. From this equation, I'll put the value of x1 here. So this is my first step. I'll give x1 equal to 0. So I'll get x2 as 5. Right? Then once you get the value of x2, you got the value. Let's assume I assume this as my u, right? X1 I assumed as u. So what I can do here, I got the value of x which is x2 for me, u which is x1 for me. I got the value of x1 and x2. I can put this in this second equation, which is the derivative in terms of x, which is x2. I can calculate the value of lambda. Let me just see. So before you calculate the lambda, you need to see, because now you have already got the values of x1 and x2. You need to see whether this inequality is feasible or infeasible. Let's say if this is less than equal to 0 at this values of x1 and x2, you do not need this inequality equation and you do not need to add the penalty also, right? So I can just quickly check whether h x1 comma x2 is less than 0 or not. So basically here x1 is 0 minus 0.2 into 5 minus 3. I think this was plus, I made a mistake, but anyways. And this comes out to be 1 minus 3, which is minus 2, which is less than 0. Right? So this is anyway getting satisfied. So then you do not need to add the penalty, right? So my derivative with respect to x2 should be 2x2 minus lambda, and this penalty term, because this equality is satisfied, I forgot, this is my step 1, this is my step 2, and this checking is my step 3, and then this is basically my 4th step, and this I can equate it equal to 0, and from here I'll get lambda is equal to 2x2, which is 10 in this case, right? And then what you will do here, what's the next step? The 5th step, which was to calculate dl by du when you know all the terms. So u here is, in our case, u is basically x1 here. So our x1 will be 0.5 x1 minus lambda is equal to, so this x1 is 0 initially, so this will be 0 minus 10, this is equal to minus 10. And what you will do here, you will calculate now the last step is x1 new is equal to x2 old minus some beta, that is just the step size, and dx1, which is basically x old initially I assumed 0 minus beta, let's say I take a small step size into dl by du, which is minus 10. What does this give me is basically 0.01. Right? So now x1 new is 0.01. I'll again go back and do the iteration till I get this dl by dx1 close to some tolerance epsilon. Do you get this iterative step? Let me show you through the MATLAB code and give you a feel of it. Wait. So this is so this is my first. So what I did, I am actually doing the same thing what I just mentioned here. If only condition is if, let's say that in this slide, if you see that this inequality is violating, then you have to add this penalty here. And then once you take the derivatives, you have to incorporate the impact of this penalty here. That is important to note. So that's what I have done here till because I'm writing it in reverse sense. So that's why it is x3 greater than 0. It is actually less than 0. I means I have just written it in the reverse sense. So I have taken this as a constraints, I'm doing the same thing. The dl, dx, x1, everything is same. And if I have the penalty term, then I'll take this in the sense of penalty. So now if I run this code, you will see that so I'm giving this problem for 10,000 iterations. I think now it has stopped. So you see here that we knew that our solution is going to be 2.5. So you see initially I started from 0. It is increasing, and eventually it is getting saturated at 2.5. So that's what the solution we got, right? So this solution is arriving at 2.5, and this is how it converges. Do you get the idea? How we do this optimization. It is a bit tricky. Please do follow these steps. You will be able to do it. You will be able to solve it. And again, so I'll not go into this, but just to quickly give you an idea, because I'm coming close to the end of time, but I'll try to, because I just wanted to tell you Newton's second order also. So here, this penalty approach is actually a soft approach, right? There can be, and converting a binding equality is a hard or exact enforcement. It has a disadvantage from the matrix size, from the mathematical or computational time point of view, and even the choice of alpha that is the penalty coefficient, is not easy, right? It is very difficult. So this is very difficult. Even also the choice of beta is very difficult in this case, and the Newton's first order generally gives a poor convergence for a big or for a complex problems. So therefore we go for so basically therefore first order gradient methods are generally least popular in the optimization area. The most popular one is, I'll just close with this. I hope I can take 5-10 minutes extra. So I'll just close with the Newton's second order gradient method. So what we can do here, instead of solving x1 and x2 separately, what we can do here, we can solve all the variables, that is x, u and lambda, in one go, if we can do that. So basically, what we can do here is optimality condition is gd equal to dl by dz, that has to be equal to 0, that is the nonlinear set of equations. Using the Taylor series expansion and neglecting the higher order terms, we can get that 0 minus delta z. I'm just rushing it up, but just trying to visualize that we'll get the minus dl by dz. This is nothing but the gradient function. And d2l by dz square is actually known as the Hessian matrix, right? And I can, because GD specified is equal to 0 here, so this is 0 minus calculated, it should be equal to Hessian into delta z, and this delta z incorporates all the variables here. So what we are doing here, that in this second order case, we are not solving x1 and x2 separately and iteratively. Here all the variables are getting solved in one go. And just to tell you the steps, we'll take the derivative with respect to lambda, we'll take the derivative with respect to z, right? And again, the penalty will be added only when your violation happens. So you'll choose an initial value of z, you'll evaluate the gradient vector, right? You'll check for convergence. If not, form and factorize the Hessian matrix. You'll calculate the delta z, which is basically delta z will be Hessian inverse into the gradient vector. So that's what we have seen previously. And you'll update the z, that is z nu equal to z whole plus beta into delta z. You'll keep on updating it till your delta z or the gradient matrix uh, is below some tolerance, and then you will stop the iteration. So I don't have time, but I will quickly tell you, and this has a very powerful convergence, and it also handle. There is still a problem how it handles inequality constraints. For to solve that, there is another method called interior point method. That's what I planned to complete, but I think I took extra time in the first example. But I'll just quickly tell you the MATLAB code when we solve the same problem using Newton's second order. Uh, you will see that the solution, why we are not getting the plot, okay. So you see here, eventually the solution reaches to 2.5. This solution is 2.5, right? Eventually it reaches 2.5, but it takes lesser iterations. So it took around 400 or 500 iterations here in Newton's second order, whereas in Newton's first order, it took around, you can just quickly see here, uh, So you see here it took around 5,000 iterations to reach the value of 2.5. So you see the Newton's second order can increase the convergence 10 times faster than Newton's first order method. And again, because we are adding this penalty function here in the Newton's second order, and this penalty function is actually still creating the problem in terms of handling the inequality equation, and this can easily be handled by interior point method. This is another method we plan to cover it up, but again I did not have time. I'll not go into these details, but I'll ask Professor Satish to explain this. I just wanted to explain the convexity also, but again I did not have time for this. I hope I can close here, or do you want me to continue? Students, okay. So Ratan is saying to continue. Okay, let me. Okay, Gaurav is saying to close. Okay, Anand is saying one more lecture. Okay. Uh, Okay, let me talk to Professor Satish and get back to you on this. Maybe later sometime I can take more lecture. So let me just stop here then. Uh, I think it's too much for one day, and it would be not good to unnecessary overload you with the concepts. So any doubts, any queries, please do let me know. Anyone? Any query? Okay, meta heuristic. Yes, if you want, we can do meta heuristic also. I can, although it is not covered today, but if you want, we can definitely think of doing a meta heuristic also. As of now, it is, I have not mentioned it in the current slides, but we can do meta heuristic also. That is much more simpler than the classical method. So these methods basically include first order, second order. These are classical methods. Okay. Any query?
Hello.
Hello. Yes.
Sir, when we are dealing with the distribution system where so many constraints are involved
Okay.
and objective function is too much non-linear and discrete.
Yes.
So how we design problem formulation, sir?
So, okay. So, are you from the distribution company?
No, sir. Scholar of this power system only.
Okay. So basically, okay, ठीक है, got the point. So basically, obviously, the distribution system is having a lot of nonlinearities because we cannot model them as a linear system or DCOPF. It has to consider all the AC, real power, reactive power, voltage, transformer taps, capacitor banks, inductors. All those factors has to be considered. If let's say you model the power balance equation as the trigonometric function, it will be even more difficult. If you want to model it as an unbalanced system for each bus, then you will have three further power balance equations. So you see, as we keep on incorporating things, it will become very difficult. Frankly, it is very difficult to handle nonlinear optimization problem in any method I use, interior point, Newton method, Newton second order. We need to be uh, uh, smart from our sense so that we can minimize the burden of the nonlinearity. For example, let's say I always recommend to the student, instead of going for trigonometric expressions, you can go for rectangular form of power balance equations. Once you go in the rectangular form of power balance equations, things are becoming relatively simpler compared to the trigonometric equation. Although we do not solve Newton's first order and second order method per se, we do not write a code for it. We use, maybe you can use fmincon in MATLAB, or maybe if you are having GAMS, I'm sure you have GAMS in your lab. So you can use GAMS for solving nonlinear optimization problem. But once you convert all the trigonometric equations into the rectangular form, you make the problem simpler for all these solvers, which are either from interior point of view, or either from fmincon point of view, or the GAMS solver point of view, or any other open source solvers you use. It will become simpler for them, these solvers, to implement your nonlinear optimization problem. But in general, nonlinear is not easy. I can say that for a small system, yes, it may work, but for big systems, again, it may take many time or infinite time to converge. I know for my few of my optimization problems, what my students are doing, it is taking around a day or two to converge. So we can never say. And on top of that, if you add the mixed integer or binary variables on that, again, it will be even further slower. So it is very challenging per se.
Yes, sir. Yes, sir. Thank you, sir.
Thank you, Anand. So shall we stop here, or any other queries you have? I can stay for a while. Jyotika, are you there?
Yes, sir.
Okay, so shall we close, or what shall we do?
We'll close the session, sir, if nobody are having any doubts.
Okay, perfect. So thank you, everyone. Thank you so much for your time. I'll talk to Professor Satish if there is any further session I can take. It was a really nice interacting with all of you, especially Anand, Rutvik, Gaurav, Ratan, for actively participating in all the questions. Thank you so much. Thank you so much, everyone.